All right, let's dive into the secret life of one of the most important elements in the universe. It connects the fuel that powers your car, the plastic that makes up your phone, and even the very DNA that makes you, well, you. We're talking, of course, about carbon. So, just think about that for a second. What on earth could possibly link gasoline, a phone case, and the building blocks of life? They seem like they're from completely different worlds, right? But believe it or not, they all share one single, fundamental ingredient. And there it is. The answer is carbon. It's like the universe's ultimate chemical architect, the backbone for pretty much all organic life. And we're about to take a tour through its absolutely incredible story. So our journey into carbon's world, it starts deep, deep underground with the so-called black gold that has fueled, well, our entire modern civilization, crude oil. This stuff is where it all begins. But crude oil isn't just one thing. It's this messy, complicated soup of different molecules called hydrocarbons. It's basically the ancient cooked-down remains of tiny organisms like algae and plankton that got buried millions of years ago. All that heat and pressure turned them into this raw material for so many things we use. So, how in the world do you turn that black sludge into something useful? Well, the magic trick is a process called fractional distillation. First, you heat the crude oil up until it's super hot. Then you pump that hot mix into a huge, tall tower, a fractionating column. As all that hot vapor rises, it starts to cool down. And here's the genius part. Different molecules turn back into liquid at different temperatures. The really short, light molecules shoot all the way to the top. That's your gasoline. And the really long, heavy gunk, like bitumen for roads, stays way down at the bottom. It's a brilliant way to sort molecules just by their size. Okay, so from the massive scale of an oil refinery, let's zoom in. And I mean way in. We're going down to the atomic level to really understand the building blocks of all this, what I like to call carbon's chemical Lego. And here it is. This is the secret sauce of all organic chemistry, the covalent bond. You can think of it like a team-up between atoms. Instead of one atom stealing an electron from another, they decide to share a pair. And that sharing creates this incredibly strong, stable link. It's the glue that lets carbon atoms chain together to form millions of different molecules. Now, because carbon is so good at forming these chains, we get this really cool organizing principle in chemistry called a homologous series. Honestly, the best way to think about it is like a chemical family. All the members of the family might look a little different, but they share the same last name, they follow the same family rules, and they all act in pretty similar ways. And just like any family, they've got rules. Every member of the family has the same basic setup or functional group and fits into the same general formula. The main difference is that each new member is just a little bit bigger than the one before it, by exactly 1 carbon and 2 hydrogen atoms. This means they all react in similar ways, but their physical traits, like their boiling point, change in this really nice gradual pattern. This is a perfect example. Let's take a look at the alkane family. You start with methane, just 1 carbon atom. It boils at a chilly minus 162 degrees Celsius. Now, just add 1 CH2 group and you get ethane. Suddenly, the boiling point jumps up. Add another, you get propane, and it goes up again. You see that pattern? The bigger the molecule gets, the higher the boiling point. That's the homologous series right there in action. So, why does that happen? Well, as you keep adding more carbon Lego bricks, the chains get longer and longer. And these longer chains have stronger forces of attraction between them. That means you need more energy, more heat, to pull them apart. That's why their boiling points go up and they get thicker or more viscous. And that super simple principle, that's exactly what makes that whole distillation tower work. It all comes down to this. Right, so we've met the alkanes, kind of the most basic family of hydrocarbons. But carbon's world is packed with interesting relatives. Let's go meet a few more. Let's compare the alkanes to their more energetic cousins, the alkenes. The absolute key difference is the bond. Alkanes are saturated. They're full up with hydrogen atoms and only have single bonds between their carbons. This makes them pretty stable, pretty chill, but alkenes are unsaturated. They have at least 1 carbon-carbon double bond, and that double bond acts like a chemical hotspot, just begging to react with something. And you can see that difference clear as day right here. On the left, that's butane, a classic alkane. Notice all the single bonds. On the right, you've got but-1-ene. See that double bond right at the start? That one little change completely transforms the molecule's personality. It's a total game changer. And you can extend this logic to all sorts of other families, each one defined by its special little attachment, its functional group. For instance, you tack on an OH group and boom, you get an alcohol, like the ethanol in antiseptic wipes. Or you add a COOH group and now you have a carboxylic acid, which is what gives vinegar that sharp kick. Each little group gives the molecule a whole new identity. Okay, so we have all these different families of molecules. But how do chemists actually build things or change one thing into another? Really, the entire art of chemistry boils down to just one thing: making and breaking bonds in a very controlled way. And not all bonds have the same strength. I absolutely love this analogy. Think of bonds like panes of glass in a window. A single bond, that's like a single pane, fairly easy to break. A double bond is like double glazing, way tougher. And a triple bond, that's like high security glass. You need a massive amount of energy to shatter that thing. Now, one of the most common ways we break bonds is just by burning stuff. That's combustion. And the outcome depends completely on how much oxygen is around. If you have plenty of oxygen, you get complete combustion. Think of that clean, efficient blue flame on your gas stove. It just produces carbon dioxide and water. But if you starve that fire of oxygen, you get incomplete combustion, that nasty, sooty, yellow flame, and it creates some awful byproducts, including poisonous carbon monoxide. Industry needs to break bonds too, but with way more precision. And that's where a process called cracking comes in. Basically, inside these huge reactors, they take those really long, heavy, not-so-valuable hydrocarbon chains from the bottom of the distillation tower. Then, using crazy high heat and a catalyst, they literally crack them apart into smaller, much more valuable molecules, like the short chains we need for gasoline or those super reactive alkenes that are the building blocks for plastics. All right, we've seen how the bonds get made and broken. So for our final section, let's zoom back out and see how all this microscopic chemistry creates the actual, tangible world that we see and touch every single day. Up to now, we've mostly talked about the super strong covalent bonds inside the molecules. But what about the forces between different molecules? They're much, much weaker, but they can have some seriously powerful effects. My favorite example? The gecko. This little guy can just casually walk up a perfectly smooth wall, defying gravity. How? Its feet are covered in millions of microscopic hairs. Each tiny hair creates a teeny tiny attractive force with the wall. One of them is nothing, but the combined effect of millions of these little forces all working together is strong enough to hold up the whole gecko. It's just a masterpiece of natural engineering. So just think about the journey we've been on. We started with the ancient remains of life, buried for millions of years. We've learned how to sort those molecules, crack them apart, and then rebuild them. We've turned them into fuel, into plastics, and even into the subtle molecules that give us the smell of a rose or the taste of raspberry. The incredible story of carbon really is the story of our modern world, and it leaves you with one big question: what are we going to build with it next?